My name is Attila Szegedi. I'm a staff engineer at Twitter. I'm working at Twitter's runtime systems team. Our responsibilities include, well, maintaining the runtime systems that are used at Twitter. These days, this mostly means, well, both Ruby runtime in ever-decreasing amounts, and on the other hand, as the Ruby usage is going down, the JVM usage at Twitter is actually going up. So this is ever increasingly means our responsibility is actually maintaining JVMs at Twitter. Now, well, of course, what is there to maintain with a JVM, right? So it's not so much maintaining JVM as actually making sure that when people deploy their applications, then they run nicely. Now, for the realities of the hotspot Java runtime, which is what we use at Twitter, is such that, well, you have to tune things and you have to optimize things, and we'll get into a lot of those. Most notably, people will come and come to our team mostly when they are finished coding and when they believe they are done, and there is a interestingly big gap between something being done and something being production ready. And usually they will face the problem that the beautiful code that they have written suddenly does not perform so well in production. And that's when they call us in. And I've been working for Twitter for well more than a year now, year and, well, 15 months. And I've seen the good, bad, and the ugly. And this presentation is titled Everything I Ever Learned About JVM Performance Tuning at Twitter. I actually like to run it with the alternative title of More Than I Really Ever Wanted to Learn About Performance Tuning at Twitter. So, Twitter's biggest enemy, as most highly trafficked website, is not surprisingly latency. For everything that's user-facing, be it a web browser or a Firehose stream by somebody who licenses it, really want to make sure that whatever is tweeted is fanned out and delivered to all the clients as soon as possible. Then when those clients connect to us, that we are responsive. And that's a primary optimization. So your business might be optimizing for different aspects. Twitter is optimizing for latency. And now we have looked into the contributors to latency. Not surprisingly, the biggest ever contributor to latency in a JVM is the garbage collector. You have few others, but they are usually orders of magnitude less significant. You can have problems with your inter-thread communication, any kinds of locking, synchronization, thread scheduling, and so on might contribute. I/O can contribute. Your application algorithmic inefficiencies can again contribute. However, this talk is not about those, because you cannot fix those by tuning the JVM. You fix application algorithmic inefficiencies by fixing your application. You fix I/O. I/O is mostly in the domain of your devices and your operating system. You can actually help something with the inter-thread locking. We'll get to that maybe if we have enough time. So the areas of performance tuning normally are memory, lock contention, CPU usage, and I/O. Now, I will concentrate mostly on memory tuning in this talk, and probably will get a little bit into the lock contention tuning at the end. I won't really be dealing with the other two. There are multiple reasons for that. CPU usage tuning, we don't really often tune for that for the sheer reason that we are normally not CPU bound. We will ultimately be I/O bound in most cases. Now, if we concentrate on memory, this again has several areas. You can tune for memory footprint, and you can tune for basically having your application use less memory. You can tune for allocation rate, how many objects does your application allocate, at what speed. And finally, you can also tune the garbage collector itself, so that when it actually has to deal with the garbage, how fast can you get rid of it. All right, let's look into these one by one. Memory footprint tuning. This is really significant because your garbage collector will be a source of latency. The best way to make sure that your garbage collector is impeding you the least is to make sure that it has least work to do. The less memory it has to manage, the least work it will have to do. So there is a really blatant sign that your application is too big. That's if you get an out-of-memory error. This normally has the three reasons. You can't have too much data in your memory. We'll get to what too much means. Your data representation might be inefficient, which I normally refer to as, I normally tell the developers that, your data is fat. They usually have a your mom joke in response. That's why it's good to work in a company where most of the people are young. And you can also have a genuine memory leak, but again, that's an application problem, not a tuning problem. We won't be talking about that. So what's too much data? Normally, how do you diagnose these things? Well, just staring at the GC logs gets you a long, long way. One simplest thing you can do, you run with verbose GC, and then you just observe your numbers in your full GC messages. You have, this was my memory usage before GC, after GC it's some other amount, and this is the total allocated to the JVM. And this is the number that you're interested in. This is your live set, right? Now, when you run out of memory, the questions are, can you give the JVM more memory? As a rule of thumb, the more, the better. If you can, do it. There is a separate question of how do you allocate it between new size and old size? We'll get into that. Do you need all that data in memory? Not necessarily. Do you have a lot of data that's reproducible from external sources, meaning that you actually have a cached representation of something that's otherwise fetchable from disk, recomputable, whatever? For that, you can consider using LRU caches or maybe soft references. You will notice that nice little asterisk at the soft references. I used to be a fan of them, and after 15 months at Twitter, I'm no longer a fan of them, and I'll explain why. So, fat data. Oh, yeah. Well, it doesn't necessarily manifest itself, except when you have things when our research folks come to me and they say, we would like to have our full Twitter social graph loaded in memory at once because we want to run some global analysis on it. And they say, yeah, and we have this 60 gig JVM, and it just doesn't fit. Well, yeah. Now, if you can somehow slim your internal data representation, it will work at these economies of scale. And these guys are actually loading millions of objects. If you can spare 4 bytes in every object, then you have a really sizable saving. Now, to understand this, let's see what does a typical object layout in JVM look like. Whenever you just say new Java Lang object, you will spend 16 bytes on a 64-bit JVM. I'm talking about 64-bit JVMs because that's what we use at Twitter. And probably in the coming years, you will have to use them too. JVM object headers are 2 machine words. If your JVM is 64-bit, this is 16 bytes. Or if you want it to sound even more horrible, it's 128 bits. Now, if you allocate an array, this is the most simple array that you can allocate, which is a byte array that can carry 0 bytes. That will cost you 24 bytes because there is an additional 4 bytes for the length, and then there is a padding to the next multiple of 8. And then things get ugly because it turns out that all nice things about decomposing your class hierarchy into superclasses, subclasses, abstracting away the common things into a superclass, it's great, except that there is a padding on the subclasses as well. So if you have this class, one instance of this class will cost you 24 bytes because there are 16 bytes for the header for every instance, and then there's 1 byte for the actual value, and then it's padded to the next multiple of 8. And then if you have a subclass that extends it and adds another byte field, you would think, well, yeah, sure, this still would need to fit into 24 bytes, right? Because now we have the 16 byte header, 1 byte for X, 1 byte for Y, and then you pad it to multiple of 8. Well, unfortunately, no. Because it turns out that Hotspot will actually do subclass padding, padding on a subclass by subclass basis. So basically, we'll have a padding of 8 added after all the fields of class A, and then you have 1 byte for Y, and then another 8-byte, another padding to the next multiple of 8. So actually a new instance of class B will take 32 bytes. Obviously, Java does not have inline structures, no inline array elements. So if you have an instance of a class and it has a pointer to another object, then this guy will take you 40 bytes because you have two objects, right? That's two headers, 16 bytes each. And this one also has a 8-byte pointer in it. And again, normally these things don't matter. When you want to do analysis on, 9 million Justin Bieber followers, then they might matter. So one thing that we did, and these are the points where you can get into really, when you are sometimes forced to get into really ugly transformations of your program. I'm not warranting you do that in general case, but sometimes you have to. For instance, the research team was able to only load all the data in memory by basically representing each Twitter user as an array of integers, and the integers were the IDs of the people that particular person follows. Because this was a constraint problem, they wanted to walk the full set, and they wanted always to walk it linearly, so it worked. It does not necessarily work. It works if you have some nice constraints on the usage of your data. I told them, I was telling them that, if Twitter grows at the pace that it grows, and we don't get bigger machines with more RAM, we did actually in the meantime, then you guys might, resort to having to use differential delta encoding for the arrays. Them being researchers, they actually really like the idea. One good thing you can do is that you can use compressed object pointers, and these are actually enabled by default on recent Java 6 versions, in which case pointers become 4 bytes long. The trick is that when they are dereferenced, they are always shifted left 3 bits because every address is a multiple of 8 anyway. So that way you have 4 billion different addresses multiplied by 8. You can actually address 32 gigs of memory, which is nice. So if your -XMX setting is less than 32-ish gigs, it actually works until 30 gigs automatically, and after that you have to explicitly specify it on the command line. You will get a little bit more compact representation of your code. However, this also means that there is an uncanny memory performance valley between 32 gigs and 40-something gigs, because under 32 gigs, your JVM will internally compress every pointer to 4 bytes, and that some Oracle studies have shown that in a typical application, it can result in about 30% less memory needed to store the objects. And typically, it depends on what's your mixture of classes and how many pointers are there versus primitive fields and so on. But 1.3 is the usual multiplier. This also means that when you go from 32 to 33, then suddenly the JVM will stop using compressed pointers, and you will be able to store much less objects than you used to. The moral of the story is, if you need more than 32 gigs of heap, well, then your next stop is 48 or above that. Anything in between will actually give you less. This is just a handy chart about various structure sizes with compressed pointers and uncompressed pointers. Won't go into this now. Oh yeah, one hint that, this sounds so straightforward that I'm actually a little bit ashamed to even have to talk about this, but, avoid using instances of primitive wrappers. Normally, you don't really do this explicitly, but sometimes some libraries will do it for you. One interesting tidbit that I discovered with Scala 2.77 was that if you declared a type to be a sequence of int, it will internally store boxed integers. And if you declare it as an array of int, then it was storing primitive integers. And now the second only needs an array header plus 4 times the length of the array for the elements. And the other will also need an array header plus a pointer to the integer plus the integer instances. It's much worse. Now, obviously, and I'm not bashing Scala. A lot of Twitter code is written in Scala these days. We have a lot of developers who really love Scala. However, the moral of the story here is not Scala is bad. They fixed that by Scala 2.8, by the way. The moral of the story here is you never know what do your third-party dependencies actually do. And when things start being fishy, the only real way to figure out what they do is to profile your code. So this specifically, I found out using a profiler. There was a JVM. It was running the application that was performing terribly. And when run under the profiler, there were just bazillion instances of Java-lang integer. And then you catch the smell and think, OK, so what's this thing doing? Yeah, just what I said right now. You don't know the performance characteristics of your libraries. You will only know them when you run your code and when you profile. Either that, or read the source code of every library that you use and understand it in advance. Your pick. Similar lesson goes for map footprints. Again, we also love Google Collections. And turns out that Guava's mapmaker.makeMap might take, actually, does not necessarily take, but it can take more than 2 kilobytes now per instance. This is the reason for that is that it's a concurrent map. It will create segments based on your concurrency level of your processor, which at Twitter will be 16 normally. And each one of those segments actually takes up space. So just telling Guava to make you a concurrent map will rob you of a little bit more than 2 kilobytes. Again, not a big deal, except when you discover it in Twitter's edge caching system, which is responsible for statefully storing the follower map of everybody that connects to them, and then when a tweet comes in, making sure that everything is fanned out to all the clients that are currently connected to it. And if you have maybe 1 million-ish users connected to a particular service instance, which is not uncommon, not at once, but this information is retained for as long as possible in memory, then this will blow up. So what we did is we fixed this by saying, all right, let's use a map maker with concurrency level of 1. And now, of course, you might stare at this belief. So what sense does it make to have a concurrent map with concurrency level of 1, right? Well, the nice thing about it is that it still retains the semantics of a concurrent map, meaning that if it's modified while something is traversing it, the unfortunate other thread that's traversing it won't actually get a concurrent modification exception. And we wanted to preserve this particular behavior. So this eminently made sense for us. And it was only a problem if, say, somebody unfollows you while your tweets are being fanned out. And this doesn't necessarily happens a lot because I have 2,000 followers. If I tweet something, the code will really quickly dispatch it to all the 2,000 followers. Now, if I were Lady Gaga and it has to dispatch to 10 million, then traversing that particular map might take a little bit longer time. I used to actually joke that we might or might not have a separate code path for her, but I'm not making this joke anymore because people took it seriously, and it ended up being the most tweeted thing about this presentation ever. It's a joke, by the way. All right, so Thrift. So Twitter uses Thrift for RPC, and this again goes towards the low latency theme, is that we do use queuing systems at Twitter, but we only use them when latency doesn't matter, and that's not many places. So wherever it matters, we prefer to have all the clients knowing about all the services, having load balancing in the client, load balancing and failovers in the client, and basically speaking Thrift. The things I like about Thrift are exactly the things that I hate about Thrift, and that is that its wire format is not self-describing on the wire. That's a good thing because the messages are really compact. It's a bad thing because upgrading versions and so on is really painful. Plus, you need to have code generators to actually decode your messages when they come off the wire or when they go to the wire. Now, you always have few people who will have this genius idea saying, oh, look, Thrift generated my classes already. I mean, I'm shipping things like person or geolocation or whatever on the wire, and I need to use it in my domain model. And Thrift just generated something which has exactly the right name and the exact right field, so I'll just use them in my domain model. That's almost never a good idea for many reasons. One reason is that Thrift auto-generated classes were generated for transport purposes, and they have baggage. Their baggage manifests itself in the form of a bit set. Every Thrift class, generated class, that has a primitive field will have a bit set that one bit corresponds to each primitive field, and it tells you whether the value of that field was set or not. Because in Java, right, you cannot distinguish between 0 and false and field not being set. There's no primitive notion of null. And that's why, and Thrift wants to be compact on the wire, so it will sacrifice some space in memory in order for it to be compact on the wire. So it won't be serializing those fields that are not being set. Now, the problem with this is that having this bit vector, this bit set, will take away 52 to 72 bytes of overhead per object. 72 if you don't use compressed pointers, 52 if you use. How does it manifest itself? Here's your Thrift-generated object. You have a pointer to a bit set vector, 8 bytes. You have a bit set, 16 bytes for a header, 8 bytes to a pointer to an array, and another 4 bytes for the number of words actually used in the array. And then finally, the bit set has an array of longs, which is 24 bytes for the header, plus 8 bytes for a single long, and then there you have that one bit that is actually being used. Is it okay? Yes, of course it's okay. It's an end to a means. If you only use your Thrift objects on your request-response boundary, meaning your Thrift deserializes your data on the wire into object, you read them, do something with them, you generate your response, you send it, and after that you forget about Thrift. You're fine. But if you're holding on to them and keeping them in memory, and maybe you have this genius idea of having a, like a Thrift caching proxy in memory that will store 20 million of these, then suddenly things get ugly. And I had a person coming to me saying that I want to store 60 million objects in memory and my heap should be big enough, but I still cannot. And then it turns out that he was doing this. And Thrift also can be heavy. It doesn't support 32-bit floats, so you are stuck with 64-bit floats. And you also miss a bunch of opportunities for interning and normalization. This is actual code from one of our systems where we were storing geolocation. And you can see that you have, this was actually generated by Thrift. So you have a city, a region, country code, latitude and longitude, which are doubles, and confidence, which is actually a value from 0 to 100, but for whatever reason, it's also expressed as a double. So obviously, you could compress this a little bit. So what I ended up doing is I told these people that, forget Thrift. OK, you have this version comes in the wire, but when you are storing this data in memory, just do some, old-fashioned database theory normalization, saying, you see, these things are typically repeated. When you have a city, it's normally resides in a single country. They don't really change countries that often, bearing wartime events and peace treaties afterwards. So by doing this, and then intern the strings, right? So with Thrift was not interning. You ended up with several millions of the strings saying UK or FR or whatever in memory. Really wasteful. And the people who were doing this, they started writing their own memory manager because they figured out that the Java memory managers actually cannot cope with their data volume, so they have to be smart about it. And that was when I fortunately intervened, restructured their application this way, and then suddenly instead of 60 gigs of RAM, they need 20 gigs of RAM, and the GC performs nicely, and with big pleasure, I deleted every last trace of their custom memory manager code in Java, which was, of course, something built on top of byte arrays and so on. Horrible. I mean, you hit people on the head with a glue stick when they do that. Another thing that you need to know of is you need to be really careful with thread locals because these guys stick around. And this is only really problematic when you have a thread pool with many-to-many resource allocation. Here's an example. We use Redis for something. Redis is great, by the way, but if you have 200 threads in a pool and maybe you are connecting to 50 Redis servers, it ends up that the JRedis library, which we're using, was using a buffer for composing the message that goes over the wire in a thread local. And then, because every thread was using every connection, we ended up with 10,000 connection buffers in memory. Basically, every thread had 50 of them. Oh, and the library allocated 24 kilobytes for the buffer. So you had 10,000 times 24 kilobytes. And it actually gets worse because at Twitter we didn't use 200 threads per VM. We were probably using 500-ish. And instead of 50 Redis instances in production, we actually have 750, so do the math. Now, at this point, you can either use synchronized objects if you want to, or you can just create new objects all the time. It's really not that expensive. Allocating a 24K array is a matter of a pointer bump in the Eden and zeroing out the memory. It's linear operation, but it's usually very fast. Actually, you can forego zeroing out the memory if the VM can prove that the memory is already zeroed out. Okay, part 2, fighting latency. And this will actually be a talk about the garbage collector. And I will have some more case studies at the end, but those case studies actually make more sense if we go through this first. So that's why the talk is structured the way it is. All right, so maybe sometime during your university studies you were being told that there is an inherent performance trade-off in systems with finite capacity between memory and time. The fact is, this is true. It's absolutely true, except that this view is convenient, but actually fairly oversimplified. I usually work with a notion of a performance triangle when I'm reasoning about these things. And the memory is memory. That doesn't change. You have a memory footprint, but time, you can actually separate it into concerns of throughput and concerns of latency. Normally what you want to do is you want to press your memory footprint down, you want to push your latency down, you want to increase your throughput. Now this again, this is a better model, but it's still, you have to keep in your mind what is that you want to increase and what is it that you want to decrease, because then you sound stupid when you speak with your colleagues and you say, yes, we need to increase the latency. And then, no, other way around. So that's why I normally came up with expressions compactness and responsiveness to speak about. Compactness is basically the inverse of memory footprint. The application is more compact if it uses less memory, and responsiveness is the inverse of latency. It's just how fast do you perceive that the application responds. Now, for a particular combination of your application, your JVM, your operating system, and your hardware, you will normally have some fixed value that's the product of these three factors. And what I normally refer to as tuning is that for this fixed value of these three factors, you can increase one while decreasing the other two. And there is also the matters of optimizations. That's normally when you somehow figure out a way to increase A. You put in faster hardware, you have a better compiled kernel, your JVM has improved, or you improved your application. These are optimizations. Everything else is tuning. All right. Okay. As I said, you can trade one for the other within limits. Unfortunately, you cannot bring anyone to zero by just pushing any other to really high normally. Sometimes if you have spare CPU, you can actually get to some pure win-win situations. There are not too many, but there are. So what do I refer to when I speak about responsiveness versus throughput, right? This is the profile of a high throughput application where requests are being processed one after the other. So it has high throughput because it processes many requests, and then sooner or later one of these requests will suffer a real bad pause, or several of them will actually suffer it while it's garbage collecting. A low latency application will have lower throughput. These request responses are spaced apart. And each one of them incurs a little bit of an additional latency, but the worst case latency is much lower. And what's even more important, the performance of your application is more predictable, right? If you have something that performs like that, then if you put in faster hardware, you will normally see linear improvement. If you have something that performs like that, it's not really clear what will putting in more hardware buy you. It might actually buy you more throughput, and that's what it should buy you, but you still won't have a predictable latency profile. As I said, biggest threat to responsiveness in the JVM is the garbage collector. So let's see what can we do about it. It's entirely hotspot specific. Okay, Twitter runs on Sun, now Oracle hotspot. So what I'm about to tell you is everything pertains to it. I'm not talking about tuning, say, the Azul JVM. Gil will have a talk about this after mine. It will actually be a nice contrast to this talk. Normally, what happens is that in hotspot, you have 5 memory pools. You have new generation, which is composed of Eden and Survivor. You have the old generation. And you have something that's called the permanent generation, yet something that's called the code cache. We don't deal with these two. They are out of the scope for this talk. We will deal with these 3 guys here. All right. How does the young generation work? And excuse me if you know this already. It's when I'm going to speak with a new team or somebody that I haven't yet spoken to at Twitter, quite often people will write Java applications for a living and not have an idea how does the memory management in the JVM they are deploying to work. So that's why I need to expose this. So whenever you say new something, new any object, this object will almost always, except if it's really large, but let's not go into that, be allocated in this part that's called Eden. Eden is always allocated from start to the end. There's always a pointer. Left of the pointer is allocated space. To the right of the pointer is free space. So when you say you want to allocate an object, the pointer is moved to the right by the amount that the object takes up. The memory is zeroed, and the pointer returned to your application. That's it. All new allocation happens in Eden. Allocation only costs a pointer bump, plus memory zeroing, but that might happen in bulk. It's really cheap. When Eden fills up, there's a stop the world copy collection into one of the 2 survivor spaces. What this means is that there is a set of roots, the live objects, whatever is in stacks, whatever is pointed to from registers. The garbage collector starts from these, walks all the live objects, and as it encounters them, it copies them into a survivor space. And when it's done, then it takes this pointer, which is now here because we filled up, and resets it here. What this means, and this is really important, is that dead objects do not cost anything to collect. They don't have a cost. A live object that's encountered while traversing the pointer references, a live object has a cost of copying it. A dead object doesn't cost anything. It's completely bypassed during the copying, and it's completely bypassed when the pointer is reset. It has a 0 cost to collect. So you probably don't have to worry too much about garbage. Yes, you do, but we'll see about that. But normally, don't be averse to making allocations just to avoid allocation because they are costly. They're not. And after several collections, survivors get tenured into the old generation. Oh, another thing that people routinely mistake is they tell me, we are using the concurrent mark and sweep collector. It's concurrent, right? So we should have no pauses in our application. Again, wrong. Concurrent mark and sweep, which is a concurrent collector, meaning it runs at the same time as your application, so theoretically doesn't stop it. That guy only applies to the old generation. New generation is always collected using a stop the world collector. Even if you use concurrent mark and sweep, you will get stop the world pauses while your Eden and survivor spaces are collected. The good news, this is usually really quick, like 10 milliseconds every now and then, because again, the time cost for collecting the Eden and survivor spaces is proportional to the number of surviving objects, and normally most of your stuff here will be garbage. All right, so when you have a request response kind of application, what do you want to have? You want to have a young generation operation that is big enough to hold more than one set of all concurrent request response cycle objects. What this means is that if you are responding to HTTP requests and you have 50 threads and every request will maybe take 10 megabytes, then 10 megabytes time of total objects allocated, most of them will be garbage, but say you need that much. Then, what do they say, 10 megs and 50 threads, then your young generation should be big enough to be able to, your Eden should be big enough to not have to garbage collect on each request response cycle, right? So make sure that you have at least that big new size. And your survivor spaces should be big enough to hold your active request objects. The active means those that are within those 10 megabytes allocated per thread for each HTTP processor, but that are actually live at the time when the GC kicks in. Now maybe that's not 10 megs. Maybe by the time the GC kicks in, your request is halfway through and it generated 6 megabytes of garbage and have not generated yet the other 4, but maybe it has 1 megabyte of live objects, right? So, and you want your survivor space to be big enough to fit those. Now, there is not really any upper limit on how much memory in the new generation is good. The more, the better. If you can size it that you will only hit one young generation GC every 1,000 request response cycles, wow, why not, right? Most of the stuff in there will be garbage, and the garbage doesn't cost anything to collect, so you get much better throughput. All right, so when it comes to the selection of collectors, you have several in the JVM. You have so-called throughput collectors, which will give you the profile that I showed you, the first profile, where you will have no latency, then really terrible latency. You have a one-threaded serial GC. You have a multi-threaded parallel GC, which actually is only multi-threaded in the new generation. You have the parallel old GC, which actually sounds worse than the parallel GC because it has old in its name, so it's, you know, it's older. But it actually means that it also collects the old generation multiple threads, so it's actually better. And then you have the low-post collectors, which try to do most of the work as the application runs and avoid stopping the application as much as they can. There is the concurrent mark and sweep, which the correct name for it is mostly concurrent mark and sweep. I mean, seriously. And there is the G1 GC. I cannot discuss it, unfortunately. The reason I cannot discuss it is because I do not understand it. And it's really hard to tune something you don't understand, believe it or not. And the reason I don't understand it, on the other hand, is that right now I cannot seem to be able to find any literature on the actual working of the G1. The newest paper is dated 2004 or something. We did try to tune several of our systems for G1, and we couldn't. So again, I can either not speak about it or pretend to understand it, but. All right, so there's an interesting thing you can do for throughput collectors only. There is this thing called adaptive sizing policy. If you use this switch, then instead of figuring out the memory sizes, you can just tell your JVM that max GC post time in millis, 100. I never want more than 100 milliseconds spent in GC. That's actually probably very optimistic for most applications, but you know, you can try it. And you can also tell it, I don't want to spend more than, say for 19, 1 to 19 ratio of the CPU in GC. This is a latency target. This is a throughput target. And normally, you can use it with this kind of a latency target. And surprise, we actually do it at Twitter for some things. Our queuing systems actually use throughput collectors with the adaptive sizing policy. And it works like charm. We tried using CMS. It didn't work. It didn't work in a sense that it would have really ugly GC poses. Now, with a queuing system, you expect some added latency anyway, so we figured that we might as well try a throughput collector. And here's how it works. It normally keeps really low. I mean, this is, I think, 250 megs charge when it's idle. And this is the allocated and memory used before GC. Now, what's the ideal operation of a queuing system? Ideal state of a queuing system is being empty. Okay? Message comes in, message goes out, right? Message comes in, message goes out. You want to pass them as fast as you can. If you have to hold a lot of state, then you either have a big spike on the inbound, or for whatever reason, your consumers are not really consuming. You have a problem either way. But at least with adaptive sizing policy, whenever we saw spikes, we could see that the memory usage was going up and going up. And then if I had a graph of this further in time, you can already see it starting to come down again here. So when the spike actually went away, it would lower the memory usage. So bigger heaps in the old generation take longer time to collect. If you have to store your surge somewhere, it will be lists in memory, and it will need more memory. But basically, when the surge goes away, the JVM will try to lower the memory usage so that the GC poses are smaller. And surprisingly, it works. So I normally structure this talk, and I'm telling myself that you should really have a bit like a waterfall chart, or like 9 circles of GC tuning hell maybe, which is start with the easiest thing. If it works, you're done. So the easiest thing you can do is use throughput collector with an adaptive sizing policy. Just declaratively tell it, never give me more than 100 milliseconds pause, and see whether it can meet the target. If it can, you're golden. Don't do anything else. Yeah, if you have a bulk service, like we have a metadata processor that whenever you put a link in a tweet, then we will make sure that we will crawl that link actually to see whether it's malware or something else, and collect metadata so that we can actually show it in search results based on its content, even if you just put a link in a tweet. That don't even need throughput, that doesn't even need an adaptive sizing policy. It runs in the background. For everything else, try the throughput collector first with adaptive sizing policy. If it didn't work, well, then we need to go and use concurrent mark and sweep. However, no matter what you do, always tune the young generation first. And how you do that is you enable these flags, print GC details, print heap at GC, tenuing distribution as well. You need to watch your survivor sizes because you need to know what's your desired survivor size. I'll tell you about this in a moment. Interestingly, there is no such thing as a desired Eden size because I already told you the bigger, the better. The more memory you can give to your new generation, to your Eden, the better you are off. And what you see in the GC logs, if you use print heap at GC, is you see this kind of output. You see, well, your Eden space, after I collected it, 0% is used, which is normal, right? You just collected the Eden, so none of it is used. And one of your survivor spaces, one of them is always empty because one holds already some objects, and then when you collect, then they go over into the other one. And here you see some numbers saying, 77% of my survivor space is used. And you want to watch that number because what's the good value for that number? Anything that's not 100. So if it's 100, this means that your survivor spaces are small. And where do your objects go after a GC? They have to live somewhere. They will be forcibly tenured into the old generation. And you normally want to avoid that. So anything below 100% is generally fine. Tenuring distribution. Yeah. That's not so much interesting from point of view of tuning. It shows you that in the survivor space, this many objects survived 1 GC, this many objects survived 2, this many 3, this many 4. You want a strongly decaying distribution. If your distribution is not strongly decaying, you have one of two situations. A, your application is starting up, so you allocated all your buffers and the structural objects of your application, and they're slowly going through GC cycles and eventually will tenure. Or you have a memory leak. But again, we won't talk about memory leaks here. Okay, so you tuned your young generation, right? You figure out your survivor sizes. You can give as much memory as you want to the new generation. Now you have to tune the CMS. Again, do the least work you can get away with, right? Don't get into options that you don't need. Try using CMS, without any tuning. Just say use concurrent mark and sweep GC and don't specify anything else. Start watching with dash verbose GC, start watching your GC logs. Do you see any full GC messages? No? Excellent, you're done. Again, don't do anything if you don't have to. Otherwise, if you did hit some full GC messages, then we have to go further, tune the young generation first, then come back. Now, what we need to do is, CMS has one really big deficiency. It is non-compacting, which means an object is allocated, it's left where it is in memory, bearing a catastrophic failure, which means that the memory can get fragmented. And what we want to do with tuning the CMS, you want to keep the fragmentation low, and you want to avoid full GC stops. And for first time ever in computing history, we have two goals that are not conflicting with each other. It's really great when you realize that, hey, I can actually do the two things with one strategy. The strategy is as follows. So CMS is speculative, right? it will, as you are using your application, it has to kick in before your memory fills up. Because if your memory fills up, then your application wants to allocate memory. There's no memory to give it. And then it has to wait. So it will be blocked. And the whole point of CMS is to not block your application. So it has to figure out when to start running. It's somewhat speculative. So you need to find the minimum and the maximum working set sizes. And for that, you can actually use a trick. You switch back to the throughput collector, because the throughput collector, on the other hand, it does exactly that. It doesn't kick in at all until all the memory is gone. When all the memory is used up, it kicks in then, stops the world, collects and compacts everything, and then tells you, hey, this much memory is still being used. And that's how you know how much your application is using. And then when you found these numbers, these are your working set numbers, you can switch back to CMS. And the trick, you need to over-provision these numbers by, and I normally say 25 to 33%. And this is when sometimes people look at me, at the company as well, as I telling them something scandalous. They're like, well, I measured and my objects fit in 60 gigs of RAM. And I'm giving this JVM 60 gigs. And the CMS doesn't work. Java is crap. Yep. Well, here's the problem, right? Is that, as I said, CMS is speculative. When it needs to have a cushion of free memory that even while it's cleaning up your old dead objects, if your application needs more memory, it can allocate from that cushion. That's what it does. If you don't give it any cushion, then it cannot concurrently clean up while still satisfying your requests. And that's this 25 to 33%. That's a genuine memory time trade-off. You will have to give your JVM more memory, and yes, for sure, a lot of that memory will actually not being used, but what you get in response is low latency because you don't get catastrophic GC failures. When I say catastrophic, this means that when a CMS miscalculates itself and for whatever reason cannot give you memory when your application requests it, so it still didn't clean up enough, or it's just fragmented beyond help and just doesn't have a chunk big enough to give you, then what it does is says, well, push comes to shove, stop the world, and then compacts everything. Then it moves the objects. But depending on your heap sizes, you might be looking at, I've seen things like 2-minute garbage collection poses. You don't want that. It's ugly. It's really ugly. And there's other thing you can do. There's this initiating occupancy fraction, which tells the CMS when to kick in. So how filled up the old generation has to be percentage-wise in order for it to kick in. And if you over provisions for 25%, then set it to 80%. If you over provisions 33%, set it to 75%. The thing is, if for whatever reason you still have problems, you can even lower it all the way to 0 if you want to. And this means that CMS will be scheduled, not always, but as frequently as the JVM otherwise can schedule it. If you have some spare CPU, it can be a pure win. Unfortunately, mostly it isn't. I'm just telling you that, you see, we allow in the lower rungs of hell here. That when you are trying things and they might work or they might not work, is that CMS is mostly concurrent. It does have some shorter phases that actually have to stop the world. And if you put it down all the way to 0, you will have these short pauses basically all the time. You have to calculate with that. Now, if your responsiveness after doing all of that is still not good enough, then you might have too many live objects during your young GC. As I said, your young GC collection time is proportional to the number of live objects. If the generational theory, most objects die young, is true, then you don't have a problem with that. If you do, then you might actually need to reduce your new generation size and reduce your survivor spaces. What this does is that if there's not much space in the new generation, objects get kicked over to the old generation really soon, and then they are left to the CMS to deal with them, hopefully concurrently with your program. You might be in a situation where you have too many threads. At Twitter, we used to have a service that's actually doing the push notifications to the push-enabled clients, which these days are mostly all clients. It used to be written with blocking I/O. I'm happy to report it's using non-blocking I/O now, but while it was using blocking I/O, it was not uncommon to have 8,000 long-lived threads on serving persistent HTTP connections. And when a GC happens, every thread stack has to be walked to determine the root live object set from those threads. With 8,000 threads, it will take time. It might impact your latency. So what you can do in this situation? Well, if you can reduce your concurrency level, and if you still need that many concurrent connections, well, split it into several JVMs. Sometimes the correct solution to the problem is not thinking within a single JVM. Sometimes the correct solution to the problem is, spin off several JVMs. Yeah, and then the really exotic stuff, like CMS has something that's called the abortable pre-clean phase. And this is something that's allowed to run for 5 seconds total. And that's something that happens before a particular stop the world short phase. And it tries to do a little bit of a cleaning in the new generation before it uses it as a global input to a parallel but stop the world marking phase. And if it aborts, meaning it couldn't finish its job in 5 seconds, it's concurrent, so it won't stop your application for 5 seconds. But if you get this message, abortable pre-clean phase aborted, it again means that you have too many objects in your new generation. And this affects the subsequent stop the world phase and makes it longer. So if you get abortable pre-clean aborting, means you have too many objects in your new generation. All right, that's all I had on GC. How are we faring with time? Because I still have one. 10 minutes? Excellent. All right. So, yeah, now you have a fairly good idea about how my days look like at work. Okay. All right, as I told you, there are other sources of latency that are not necessarily GC related. One of those that comes up fairly often is things related to thread coordination. What you need to know is that when you need to coordinate the work of multiple threads, okay, so the best way to coordinate threads is if you do not need to coordinate them, okay? So we can put that aside. If you can have your processing running on isolated threads that never communicate with each other, you're golden. If, for whatever reason, they need to communicate, well, in Java, the typical thing that you use is the synchronized keyword. And you don't always have to go for it, because synchronized actually has associated costs with it. Aside from acting as a mutex, right? Synchronized is also a read barrier on the entry and a write barrier on the exit, which means that it has it might have quite bad effect on your CPU caches. And sometimes you might find yourself in a situation when you need a half barrier. Say, you have a producer-observer pattern. You have one thread that's just producing values. This thread only needs to affect the write barrier whenever it produces the value. You have the observer. The observer only needs to go through a read barrier before it reads those values. It doesn't have to go through both the read and write barrier, so it doesn't have to go for full synchronized. Now, fortunately, the new Java memory model, volatile variables can be used as half. Volatile variables actually act as half barriers. Reading from a volatile variable is a read barrier. Writing to a volatile variable is a write barrier. So if you know what you are doing, a very big stress on know what you are doing, then you can actually use volatiles as half barriers. Then there is a surprisingly common case of the atomic update of a single value, right? Again, you do not really need a volatile for that, a synchronized for that. You can just use the JDK provided atomic, integer, long, whatever else, compare and set for that. Again, stress is atomic and single, right? Because if you need to have a coordinated update of multiple independent values, then you still need a synchronized block. Except if your atomic value is actually a composite value. Let me give you an example. You might have, say, a counter with a timestamp, okay? So that's two values, one long for the timestamp, one long for the counter, and you want to update the timestamp whenever you update the long. And for whatever reason, you would like this update to go consistently. and atomically. And all right, admittedly a contrived example. Now, obviously, you cannot use two atomic longs because you can do a compare and set on one, then a compare and set on the other, and somebody might actually observe the two separately. However, what you can do is you can declare a class. A class could be named, well, counter with a timestamp, right? That has these two fields in an and make it immutable. Make it immutable by all means. And then you have one instance of that. You read it. You create a new instance with the new timestamp and increased counter. And then you can use atomic reference compare and set to have a place where you are keeping the instance of the counter to swap in your previous value with your new value. And if it fails, then you need to repeat the process. So when you have atomic update, so you have to distinguish between coordinated update of independent values and an atomic update of a single value that happens to be composite, right? And for that, you can use atomic reference with your classes that represent the composite values. Oh, and here it is, what you were asking about. So as I said, CMS does not do compaction, so it's prone to fragmentation. And we had a really long fight. My colleague Chris Goffinet was a real champ when it came to fix this. He is one of the Cassandra committers. We had really bad performance of Cassandra. What you need to know about Cassandra is that we use it extensively at Twitter. Cassandra is used for many things. One of the major uses is storing all the values from our system-wide monitoring system. Twitter is now 10,000 machines plus in its data centers, and we are collecting statistics. I think we have about almost 2 million writes per second right now for our internal metrics. It's actually quite staggering, and this is handled by a cluster of, I think, 200-ish Cassandra machines right now. And it used to have really bad performance because Cassandra will buffer column values in memory and then periodically flush them to disk. However, this was a lot of small objects were being allocated and they were terribly fragmenting memory. So these guys eventually started using a slab allocator. When you would say, all right, I will be writing to disk. I'll just allocate a chunk of 2 megabytes. And whenever I need to write something there, I will just write it into this 2 megabyte slab. And when it fills up, I flush it to disk. Now, normally, I'm a big opponent of any custom memory management schema. However, this has a very constrained use, and that's what makes it valid. So generally, you should not be writing your own memory manager. If you're getting to a point where you say, I will want to release these objects, if you're thinking in objects as such, then you are already doomed, basically, writing your own memory manager in Java. However, in Cassandra, they were thinking in terms of values. So the constraints were as follows. These values would be written to disk anyway, so they have to have a binary representation, right? So it's OK to write them in a binary representation. They will be flushed to disk and never read back into the application again from the buffer. So you don't have I serialize my object into my own memory manager and I deserialize it from it. That's a bag of hurt. Okay, so that's all kinds of problems. You don't preserve identity. You have to serialize, deserialize, and it's always just written linearly. And when it fills up, it's flushed and thrown away and starts again. So for that particular application, it was valid to use a slab allocator. It's not valid to use a slab allocator as your generic escape hatch from Java memory managed heap. But if you have these kinds of constraints, it's a disk buffer, it's written to linearly, I need to produce a binary representation anyway, then it's fine. And they use 2 megabyte slab sizes, and what we got to is, before that, we would have like these half-minute to 1-minute GC pauses when the CMS managed heap got hopelessly fragmented. And this would happen once every hour. That was pretty much unusable for us. And after Chris did Chris and his colleagues did all of the tunings, and well, they're not tunings, they're actually optimizations in the Cassandra code as such, and they now ship in the Cassandra. Now we got to the point where a single JVM of those 200 JVMs that we have that are logging our metrics will hit one full GC pause in about 3 days, 10 hours, and I don't know how many minutes, don't know how many seconds. You can actually almost set your clock to it. It's so regular. And with 200 machines and these long time between full GCs, we can just afford to do a rolling bounce of these machines every now and then, which, as I heard, is actually I was speaking with someone who used to have an insight into the Oracle's strategy for handling GC and so on, asking, so when will Oracle produce a real poseless garbage collector? And then the answer was that, most of the customers actually learn to work around it. And so it's probably not too high priority. We also learned how to work around it, mostly.
So is that your workaround? You do it more often than every 3 days?
Yes. Whenever your service is stateless, you can pretty mindlessly do that. If your service is stateful, you can still do that. You can just have to account for, warm-up periods. Slide is on soft references. I told you at the start that if you have too much data in your VM, you can start using LRU caches, or you can start using soft references. And I promised you that I'll get back to that. Now that we covered everything about the GC tuning, I can tell you why I used to like soft references and why I don't like them anymore. In theory, they are great. They're like, you can implement your memory-sensitive caches so that GC actually governs when a reference is cleared. So if it needs more memory, it will clear your references, otherwise not. Now, the way it does is that when the GC garbage collector runs, when it encounters a soft reference, every soft reference has a timestamp. When was it last traversed by the application? And it looks at the timestamp to see how recent it is, and then there is a gradient, which is normally 1 second of lifetime per 1 megabyte of free memory, that says that if you have a gigabyte of free memory, then a soft reference is allowed to exist if it was last traversed within 1,000 seconds, right? And if you have 5 megabytes of free memory, then it will be cleared if it was not accessed in the last 5 seconds. It usually worked quite well. Now the problem is, if you're using throughput collector, the throughput collectors by definition only run when you ran out of memory, so free memory is 0. So with throughput collectors, soft references are basically cleared on every full GC. It doesn't really give you like a nicely graded behavior. I did try this. I wrote some test applications that were observing how does this work, and unfortunately, this is how it works. Now, you can use them with CMS, because when CMS runs, it will still have some empty memory. But here's the problem. They increase memory pressure, right? So you will have, and CMS, you already did all the over-provisioning by 25% based on your load, and now suddenly you have soft references which introduce an additional variance in your load. So they will make the behavior of CMS less predictable. And that's why generally I don't like them. And anyway, they need 2 GC cycles to actually get rid of the referenced object, because on the first GC, actually just the soft reference itself will be cleared, and then when on the next GC cycle is when the object will actually be collected. And because they increase your memory pressure and make the behavior of CMS less predictable, I generally don't like using them anymore. I mean, conceptually, they're really great. You can just declare a soft reference and let it to the GC to, manage when it gets cleared, and then you can reload from disk and reparse your XML file that you had cached and whatever. But in practice, unfortunately, we saw much more predictable, much more manageable load if we were using LRU caches on our own. All right. So that's all I had. That's everything more than I ever wanted to learn about JVM performance tuning. So, any questions? Yes?
For the slab allocation.
Oh, sorry. There was the gentleman back in the white.
Quick question on, there is another approach which is G1GC.
Which is?
G1GC.
Yeah, I told you that I cannot tell you anything about it because we don't have experience with it.
Okay. And another question was should we, as you I think already mentioned, should we also do the garbage collection in code, or we just use the JVM settings by using the JVM code deletion parameter?
Are you asking whether you should be explicitly invoking GC?
In the code.
No, you shouldn't.
Okay.
Never. All right.
Yeah, for the slab allocator you mentioned, do they do the allocation on the heap or off the heap?
I think they tested both. There's not really much difference. I think they've wrote it as a pluggable strategy, so you can use either direct byte buffers or byte buffers backed by heap. There's no.
Is there difference?
There's not really much difference because by just constraining that you are not creating a lot of small objects, but you are just writing into that buffer, regardless of where it is, you eliminated the big fragmentation. Obviously, it's marginally better if you put it off heap, but not really significantly better.
In theory, off heap should be better, right? Since you don't even allocate to the heap anymore.
It is somewhat better, but not really significantly better. There is a drawback that then suddenly you no longer can configure the maximum memory usage of your application by minus XMX, and that might be a concern for some. All right.
So I just have a question on, do you have, when you measure, you're saying you guys measure the amount of space that you use by your application.
Yep.
Do you mostly use like just monitoring and seeing how much memory it uses, or do you have some kind of a tool or some algorithm that counts the code?
No, we just see what we have in the GC logs, and there are some exotic flags that I don't know what they are, and I always promise myself that I will look them up because Chris was actually using them, which shows you some data about the actual fragmentation in the CMS, which will tell you what's the number of fragments and what's the size of the largest fragment, and then if you're running long enough, you can see it nicely decaying.
And the size of the hidden space you have, you say bigger the better, but
Yes.
But I mean, you say like 90% of the size. I mean,
No. Listen. You have 64 gigs on your machine, right? And maybe you say, all right, the OS and the assorted paraphernalia need 4 gigs. So it leaves you with 60 gigs for your JVM. And now you have to figure out how much to give to the new generation, how much to the old generation. You know exactly how much you need to give to the old generation. This is the amount that your long-lived objects will take up. And that's fairly constant, right? You measure that by running your application, let it do full GCing, and you see that. And you over-provision it by 25, 33%, and that's your size for the old generation. It doesn't make sense to give more to it because it won't really be used for anything. And everything that's left, you give it to the new generation. And that's it. There is just no upper bound on what's the good size for the new generation as such. The more you can give it, the less frequently you will have the admittedly short but still stop the world pauses. Yep.
Is it okay on a production system to do proposed GC, print GC detail?
Yes, there's no, absolutely. That's actually the only way we can normally monitor them. So you have to, the only thing you have to pay attention to is to not run out the disk space. So a rollover and automatic archival in the background are something that's a good thing to configure, and JVM supports the rollover GC log files. That's,
Can we do JMX?
But it still won't give you historical data, right? I mean, yes, we also are gathering that separately, whatever is exposed in our monitoring system. But normally we always run with fairly verbose GC logs. I mean, when GC kicks in, just the overall cost of performing the GC, just writing that additional line in the log, how long did it take, it's not noticeable. So yeah. Yep.
If you get too many messages of abort pre-clean from your CMS collector, is that indicative of a problem, of a deeper problem? Because
it's an indication that you have too many live objects in your new generation. And now, what can you do about that? It's of course application dependent, but it indicates that yeah, you have too many objects in your new generation. Okay. All right. Yeah.